Hello, everybody. Welcome to today's webinar. And I think we can wait a few more minutes because, as far as I know, up to 60 participants are registered for this webinar. Right now, we are at 30. In the meanwhile, Professor Ağaoğulları, should we start with your presentation?
Okay, Umut hocam. Can I share my presentation?
Yeah, you can start sharing, I guess. Yes, I can see it in the application window. Yes, now it's full screen.
Okay.
Oh, should we wait a little bit more or?
I think we're good to go ahead and get started.
Okay. Okay, so hello everybody. Welcome to our today's webinar organized by the chapters of the American Ceramic Society, chapters of Italy and the chapters of Türkiye. My name is Umut Savacı from Eskisehir Technical University, Turkey, and I will be the chair of the today's webinar. As usual, in today's webinar, we will have two speakers, Professor Dr. Duygu Ağaoğulları from Istanbul Technical University, and she will be our first speaker. Then we will continue with Dr. Antonio Vinci. And before continue, I just want to briefly introduce Professor Ağaoğulları. Dr. Ağaoğulları is a professor at Istanbul Technical University, where she also serves as the coordinator of the Material Science and Engineering graduate programs. Following her doctoral studies at the Istanbul Technical University, she conducted advanced postdoctoral research at Stanford University as a TÜBİTAK Fellow. As a prominent figure in her field, Dr. Ağaoğulları has received numerous prestigious awards, including Tuba Gebib Young Scientist Award and the L'Oréal UNESCO National Young Woman Scientist Award in Physical Sciences. As the head of both particulate materials and the graphene and two-dimensional materials laboratories, she leads cutting-edge projects on high-entropy boride systems, advanced powder metallurgy, and materials for fusion reactors. With 95 international journal articles and experience as a principal investigator for many research projects, Dr. Ağaoğulları is a distinguished expert in advanced materials synthesis and industrial production technologies. Before starting, I would like to thank organizers for inviting me as the chair of this wonderful webinar series. And I just want to remind you that there will be a Q&A box in the Zoom, and you can write your questions during the presentation. And after each presentation, we will do the Q&A session. And Professor Ağaoğulları, the screen is yours.
Thank you for your nice introduction. Today, I want to explain and I want to give a small talk about the overview on powder metallurgy processing of high entropy borides. As Umut Savacı explained that I'm coordinating the particulate materials laboratories in Istanbul Technical University, and through the materials laboratories, Today I want to share my experience and also literature review for high entropy borides, but of course we have time limitation and it will be short. First of all, I want to introduce high entropy alloy concept. The high entropy alloy concept is first introduced in 2004 by Ye and Cantor. As we know, in metal alloy system, so it's the traditional metal alloy system. It's based on one or two elements, but in high entropy alloys, the concept is consisting of 5 or more elements in equimolar ratio, or sometimes lower or higher than this equimolar ratio. And low entropy alloys, medium entropy alloys, and high entropy alloys are the classifications. So first of all, Ye and Cantor introduced the high entropy alloy concept, and this high entropy alloy concept is difference and contrast to Gibbs phase rules, and because this concept gives us single phase and single crystalline structures, even if it consists of 5 or more elements. So there are number of studies suggesting various physical parameters for predicting structural stabilities and phase formations of high entropy alloys. Of course, rotary rules are very insufficient to describe or explain the physical or other properties of high entropy alloys. And in that case, the two different parameters, enthalpy of mixing and also atomic size difference, are introduced for the explanation of solid solution phases in high entropy alloys. And as we know, solute and solvent obeys some rules, 4 rules in rotary rules, but valence electron, crystal structure, and electronegativity or also radius difference. But here in higher entropy alloys, we are focusing on radius difference and also omega. This is the new empirical model parameter, and also mixing of entropy. So for high entropy alloys, there are some specifications. So omega should be higher or equal to 1.1, or a mixing of enthalpy is between minus 15 and plus 15 kilojoule per mole. And also radius difference should be lower or equal to 6.6%. So in high entropy alloy concepts, also there are some core effects. For example, high entropy effect is related with the configurational entropy. So formation of solid solution in one crystal structure in one phase is restricted by some mixing of configurational entropy. And also sluggish diffusion, it means that there's a lower diffusional rate. And this lower diffusional rate provides increasing crystallization structure and temperature. So this means that shorter phase transitions, and also it provides improving the thermal stability. And one effect is cocktail effect. So here we are talking about 5 or more elements in one structure. So the unexpected synergies and unexpected formulations can be effective in this compound formation. And also lattice distortion effect. In this lattice distortion effect, the most important thing is blocking of dislocation movement. So in that effect, partial precipitation strengthening or solid solution strengthening are derived by the elemental formation. And also the different size of atoms promotes some different kinds of physical properties in the structure. And this high entropy alloy concept is important for material scientists, because we have to always alter the properties of materials for different application areas, of course. For example, high hardness, high strength, or corrosion resistance, wear resistance, high melting points, of course, chemical stability, structural stability are important for us. And in high entropy alloys, the predicted applications are in cryogenic systems or high temperature systems, sometimes electronic devices, or nuclear equipments, or nuclear fusion elements, or nuclear fusion reactors. Sometimes cladding systems in nuclear reactors are some applications for high entropy alloys. Of course, there are some different applications, but these are predicted applications, not real applications. Aerospace or refractory materials for, again, nuclear equipments. So the application area is now improving, is still improving. And I want to give a short information about the production methods. For example, the high entropy alloys are produced by powder metallurgy methods and also some additive manufacturing or arc melting methods. And also thin film sputtering, magnetron sputtering, or PVD methods are also used. And the other name of high entropy alloys previously was compositional complex materials. But after 2004, Ye and Cantor described its name as high entropy alloy. And now we are classifying these alloys into groups from 2004 to nowadays. First of all, nitrates, oxides, diborides, carbides, sulfides, fluorides, and silicides. So other concepts of 2D materials in high entropy concept is also studied nowadays. But I want to talk about high entropy diborides. These are classified as a new class of ultra-high temperature materials in the last years. And these materials have 2D boron network, and also they are hexagonal aluminum diboride type crystal structure, and they have 2D rigid boron network, and also in here there are some metallic bonds, covalent bonds, and also ionic and covalent bonding is important. So the high entropy borides are important for some possible applications. Aviation, nuclear reactors, again, cutting tools, sometimes microelectronics, solar energy systems. I don't know the real and commercial application area, but these are potential applications extracted from the literature. So in here, high entropy borides have hardness, strength, corrosion resistance, and wear resistance, chemical stability, thermal stability properties. So these high entropy boride systems are generally produced by powder metallurgy methods, and sometimes carboborothermal reduction by applying high temperature. But here today I want to focus on powder metallurgy type production systems. At the first step, of course, mechanical alloying or milling, grinding processes are applied for the initiation of powder metallurgical processes. So in that case, in mechanical alloying process, of course, there are many parameters in connection with each other. But type of milling media, material, milling speed, time, atmosphere, bolt powder weight ratio, and filling of vial, process control agent addition are also important for describing the process parameters. And then maybe self-propagating high temperature synthesis procedure can be selected, or sometimes pressureless sintering, pressure sintering methods are applied for obtaining bulk structures. Generally, pressureless sintering is not preferred. If pressureless sintering is preferred, we have to include a process control agent or an activation sintering agent into that procedure, powder metallurgical procedure, because the boride system are already individually have high melting point and very stable. So we have to introduce a pressure-assisted sintering system and also apply high temperature to that kind of materials. So for pressure sintering, the most preferred method is SPS, so spark plasma sintering. In here, the temperature, pressure, heating, cooling rate, or holding time is also effective parameters. And in literature, there are many different studies, of course, but I want to focus on high entropy borides for starting materials and SPS conditions. As you see in this table, there are different kinds of compositions, and these compositions are consisting of 5 different components. There are also 6, 8, 7, up to 13 components in high entropy boride ceramics. There are different studies relating with the 13 component systems. But I'm just focusing on 5 components here to not enlarging the composition. Here, starting materials are different, and of course, the SPS conditions are different from each other. High entropy boride ceramics concept is first introduced to Guild in 2016. Thanks to Guild and the researchers, they are enlightening our way for producing metal borides. And here, the starting materials, so I'm using my cursor now, the starting materials are individual metal borides, sometimes metal oxides and boron, metal powders with elemental boron, and sometimes metal oxides, boron carbide, and graphite. So the starting material is a so important part for initiating these bulk high entropy boride structures. At the production method, high energy ball milling and SPS is generally used for powder metallurgical process, or sometimes borothermal reduction and SPS. SHS, high energy ball milling and SPS can be used as subsequent processes. So as the SPS condition, the most used, the most changed parameters are temperature and pressure. So when we go to references, not each reference, of course, but some selected reference, Guild describe a new class of high entropy materials like ultra high temperature ceramics and produce many different compositions. And these different compositions in the XRD spectra, the many different compositions have generally is giving the single phase structure. But sometimes when we change the elemental constituent from molybdenum, tungstenum, chromium, manganum elemental structures, the system, the high entropy boride system, start to give some secondary phases, some solid solution phases. For example, titanium and tungsten, and generally chromium and tungsten. So the high entropy concept is saying us that it should be a single phase crystal structure and single crystal structure. But sometimes, according to the process parameters and selected elements, the secondary element formation can be non-avoidable. And also, when we make this XRD comparison with each other, we can see the lattice parameters and also relative density combinations. Here, even if we are using the SPS sintering system, the relative density cannot go to 99% values. The system is generally at the order of 92, 93 relative density. But of course, with the rule of mixture, we cannot completely, or we cannot truly calculate the density. So we have to use, or we have to create a different kind of measurement system. At the Gill's study, also he carried out hardness testing and making a rule of mixture and another kind of density measurement. And here at that graph, we can see that rule of mixture is sometimes showing lower density values than the experimental one. So in that case, with the formation of secondary phases, we cannot use the rule of mixture based on these high entropy borides. And here there are some different SEM images. So in this SEM image, we can see some crack points, some fracture points, and also there are lots of porosities here. So the relative density is lower, not reaching the 99% values. And the even if using SPS sintering technique, getting the relative density higher diffusional rates or higher densification rates are so hard. At the another system, high entropy boride system, studied by Zhang. For example, tantalum, chromium, titanium, niobium, molybdenum, and hafnium constituting 5-component system gives generally one single phase. But in addition to single phase, there are lots of secondary formations. For example, hafnium zirconium oxide, chromium borides, individual chromium borides, or sometimes zirconium oxide and hafnium oxide. Individual systems. So here, based on the process parameters, sintering parameters, the formation of oxides is unavoidable because the hafnium and zirconium, also titanium, have very high tendency for oxidation. And also for the SDM micrographs from Zhang, we are also seeing some hafnium-rich points like that, or sometimes niobium-rich points, or sometimes zirconium-rich points. So in our case, even if there's a solid solution in boride systems, there are some rich phases, element-based rich phases in that solid solution. And also, of course, oxides, some oxides, unwanted oxide phases, and also some different kinds of individual boride phases, unreacted boride phases. In another example of Tagliateria, again, spark plasma sintering, but it's non-reactive spark plasma sintering here. The elemental powders were used in addition to boron powder. Here, the SHS powders and SPS bulk structures are compared with each other, and also here there are some binary structures. For example, hafnium, titanium, tantalum, titanium binary structures, in very small amounts, of course, and also some individual borides like hafnium boride and some individual oxides like hafnium oxide systems. So based on the high entropy alloy concepts, the high entropy boride concept explains the formation of single phase crystal structure, but in real life, in experimental studies, it's not so easy to get just one real crystal structure and one phase. At the young study centered by SPS and under mild conditions, in this case, oxides, graphite, and boron carbides were used, and high energy ball milling was introduced, then calcination and SPS sintering. Here, the study described the differences between grinding and also ball milling procedures at high temperature in SPS system. In that case, ball milling, grinding gives the higher relative density and also hardness values. The hardness value in that case exceeding the 20 gigapascal. So this is a very good hardness for a high entropy boride system. Of course, the hardness are not really higher than the individual boron systems, but there are still inside binary and individual borides, as we see from the XRD patterns. And also, the Young make an explanation about the solid solution formation here. So he believes that the solid solution, first of all, occurs between binary system. For example, hafnium zirconium, tantalum niobium, or hafnium niobium, tantalum vanadium. Then these binary solid solutions come into contact with the during the SPS or during the high temperature procedure and formed a single crystalline 5-component system. So there are also some comparison between Rietveld methods and also some DFT methods here. The crystal structure, the microstructure phase composition contains also a little, very small amount of boron carbide. So this is the unreacted boron carbide at the system. It is not a wanted, desired phase, but this is unavoidable again during the high temperature sinteric procedure. But when we look at the SEM micrographs, we are still seeing some cracks and also some voids. So the relative density is not so high again. And in addition to literature review, I want to give some explanation about our studies, why we are doing these studies, so why we are focusing on high entropy diboride ceramics, because maybe we have boron-rich country, so Türkiye has the most important boron reserves, and in our laboratory facility, generally we are synthesizing our boride phases from oxide structures, from oxide powders. So we are not using commercial powders, boride powders. First of all, we are making our borides from related metal oxide. For example, hafnium oxide, zirconium oxide, titanium oxide, with mechanochemical procedures based on mechanical milling and also leaching procedures. We are getting transition metal borides first. Then these metal borides, at least 5 components, these metal borides, individual metal borides, are turned into high entropy borides by long-term, long-duration, high-energy ball milling procedure, up to 100 hours with a planetary ball milling, or up to 20 hours via vibratory ball milling procedures. We are making some comparison in ball milling procedures because the RPM is the most important parameter during mechanical alloying of powders. Then SPS procedure is tried. We are carrying out this SPS procedure in collaboration with Eskisehir Technical University, thanks to Kübra Gürcan Bayrak and Erhan Ayaz Servet Turan for these experiments. So after that SPS system procedure, we are getting our boride systems. But first of all, I want to show the metal boride. We are synthesizing from metal oxides to high-end metal oxides to individual metal borides. So after mechanochemical synthesis and leaching procedure, we are getting hafnium, titanium or manganum, zirconium, tantalum, chromium, different kinds of boride powders. In here, I want to mention these manganum and chromium borides. These are stoichiometric systems, but many different stoichiometric borides according to binary phase diagram. So in that case, we have to add or include some elemental boron powders to create high entropy boride system. After that, after SPS processing, we are getting 3, 4, and 5 component system. We are starting from 3 component system because in our preliminary experiments, we see that hafnium, titanium, zirconium boride is the skeleton of the system. Like Zhang previous study with the binary phases, we try to get the triple, or let's say hafnium, titanium, zircon boride skeleton system first, then increase the number of elements inside this hafnium titanium, zirconium boride system. So step by step, we include manganum, chromium, and then together manganum and chromium into that skeleton. So at the end, we can see that, yes, we have single phase high entropy boride system, and this system is hexagonal crystal structure. And also we have very small amount of hafnium oxide or zirconium oxide or binary oxide in the structure. So this is of course related with the synthesis or sometimes sintering procedure. We are studying on to avoid to leach out, let's say, these unwanted oxide phases from these high entropy borides. Then we are getting some STM micrographs. Like literature data, we are seeing some hafnium rich, zirconium rich, and titanium rich area in that 5-component high entropy boride system. So even if we can see that this is a single phase crystal structure, inside in STM micrograph, we are also seeing some hafnium, titanium, or zirconium rich systems, rich areas. So in our facility, we also created some mechanical property investigation. For example, hardness test, wear rate test. In literature, generally, wear rate is not the most important parameter for mechanical properties, but I think wear is important for some applications. For example, cutting tools or some nuclear-based applications. To identify wear rate is really important. In here, at the different kinds of high entropy borides, we are getting different hardness results, but the highest hardness result is at the order of 28 gigapascal. So the 28 gigapascal is belong to 5-component system. So we can see that from 3 components to 4, 4 component to 5, really the mechanical property based on hardness, of course, is increasing. And also for wear rate, we can see that the wear rate is going vice versa. For the 4-component system, for example, when we change the elemental structure at the 4-component system, the wear rate is somehow going double at the other 4-component system. For example, titanium, zirconium, manganum, and manganese and chromium system has very low wear rates as compared with the hafnium titanium mangan chromium system. But here at the 5-component system, we can see that yes, wear rate is really low as compared with the other 4-component systems. So in another study with collaboration with Eskisehir Technical University, we made some 6 and 8 component multi-phase high entropy boride system with the same procedure. First of all, we are synthesizing the high entropy metal borides first, then by high entropy systems are synthesized by SPS and high energy ball milling. Then we are getting some important results. When we increase the components from 6 to 8, 6 to 7, 8 to higher numbers, we can see that wear rate and hardness values are going worse. For example, when we create hafnium, titanium, zirconium, mangan, molybdenum, tungsten, chromium at the value of 25 gigapascal, but when we introduce tantalum into that system, the 25 gigapascal dramatically dropped to 17 gigapascal. So the number of elements, when we increase the number of elements in that high entropy boride system, generally the hardness and also the wear rate, please look here, the wear rate is going worse. So also we made some scanning electron microscope analysis. When we increase the number of components, include the tantalum inside that structure, we see that there are lots of voids, lots of unreacted or let's say binary or ternary solution area, but not a full 8-element or 6-element solution area. So the system is, the properties and the system is going worse by introducing additional elements. But vice versa here, the structure is also containing some solid solution regions. And also one more example for 6 and 5 component system. The procedure is again the same, but the SPS conditions are changing, of course. Then we can see that in tantalum, chromium, and molybdenum including systems, we can see that at the end, at the bulk structures, hafnium zirconium oxide and high entropy boride phases are obtained again in the same bulk structure. Here, there are some zirconium, chromium, and also some hafnium rich areas in that structure. We are also seeing some oxide regions because of the XRD says that yes, there are some undesired oxide phases inside that structure, and also we are seeing these structures like reinforcement phases here. But at the hardness comparison, we can see that the maximum hardness value is reaching 24 gigapascal, let's say. And at that part, an 6-component system has not very high hardness value than the 5-component system. So as we can make a small comparison with the 5, 6, and 7-component system in our laboratory facility, in our individual studies, we can see that 5 components maybe is the ideal component, number of components in high entropy boride systems. And also different kinds of not high entropy, but let's say medium entropy 4-component system was tried in our laboratory facilities. In a 4-component system, the maximum hardness value is again 23 gigapascal ratio. And also there are some hafnium zirconium oxide phases in addition to high entropy boride phases. Also tungsten titanium boride intermetallic phase and undesired phase, of course, is obtained during these procedures. So when we use the SEM image based on porosity and high entropy phase, oxide phase, and intermetallic phase distribution, of course, we can see the high entropy phase is the most major phase, but the intermetallic phase is again at the 15% ratio. So this is a really high amount of undesired phase. And I want to make a brief information in comparison with the literature data and also in our laboratory facility data. Thank you for your listening. If you have any question, I can answer the questions.
Thank you, Professor Ağaoğulları, for this informative presentation. And I'm looking the Q&A box, but I cannot see any questions right now. Does anyone have a question about presentation? And no one is raising hand, I guess. So for the time's sake, then I believe we can continue with our second presenter, which will be the Dr. Antonio. Okay, so we have one question right now. Monica Ferraris asked that which are the applications in nuclear application areas they are asking.
Generally, in nuclear fusion reactors, there are some plasma-facing materials. The plasma-facing materials is generally based on tungsten materials, but these tungsten components reinforce with some borides. And in nowadays, there's a not real, of course, I mentioned that there's a not commercial or real application in nuclear reactors, but there's a potential. As compared with the boride reinforced tungsten materials, high entropy borides can be replaced these kinds of tungsten based systems because the plasma facing system has some limitations, for example, high melting point or high oxidation wear resistance, high temperature resistance, chemical stability. So this is just an evaluation based on nuclear reactors. Replacement of tungsten-based and boride-reinforced composites with high entropy 5-component systems.
Okay, thank you. And for the time's sake, I can ask the second question, which is about the the effect of atmosphere during the sintering. Is there any investigations about in that field?
Generally, argon atmosphere is selected during sintering, but we didn't made any investigation on this atmosphere.
Okay, thank you. And for the time's sake, as I said, I should continue with the presentation of our second speaker, which is Dr. Antonio Vinci. He obtained his PhD in Material Science and Technology at the University of Parma in 2019, and he is currently a researcher at the Institute of Science, Technology, and Sustainability for Ceramics in Faenza, Italy. He authored over 40 scientific papers published in peer-reviewed journals and holds one patent on the fabrication of refractory composites. His research focuses on the processing and characterization of ultra-high temperature ceramic matrix composites, particularly on processing techniques such as slurry infiltration, hot pressing, spark plasma sintering, reactive melt infiltration, and polymer infiltration and pyrolysis techniques. And Dr. Vinci, and the screen is yours.
Okay, thank you very much for your kind introduction. So the title of my talk will be about characterization and processing of ultra-temperature ceramic metric composites. I will start with a brief introduction about our main fields of applications and the materials currently used, and then I will follow up with two different studies. One is based on the comparison between three processing techniques, so sintering versus polymer infiltration and pyrolysis, and liquid silicon infiltration. That will compare microstructure, mechanical properties, and oxidation resistance. The second study will be based on the use of graded structures. So we investigated both doing fiber gradients, so increasing the fiber content across the specimen, or changing the composition while keeping the fiber content constant. And then we also did some strength retention studies and arc jet testing to validate the material at the end. I apologize if you hear some noises, but there is some work in progress in the near room. So I will start with our main fields of application. So by extreme environments, we mean any environment characterized by very high temperature, corrosive atmospheres, high heat fluxes, vibration, shocks. So for this kind of application, your common alloys or polymers, they cannot withstand these conditions. So we have to move to a specific class of materials based on ceramic matrix composites. Currently, the main materials used in this field are carbon-carbon or carbon-silicon carbide composites. They are very strong and tough materials. They possess very high strength, high fracture toughness, intermediate modulus. They are relatively lightweight, but they are unsuitable above 1500 degrees C because they undergo significant ablation. And they also are manufactured with expensive techniques such as chemical vapor infiltration for the carbon-carbon composites. On the other hand of the spectrum, we have ultra-temperature ceramics. These are ceramic materials with very high melting points, above 3000 degrees C. They are very strong, very high modulus. They can maintain the strength even at higher temperature, even above 2000 degrees C. But they are very brittle. They have low fracture toughness, and also they are heavy. So if you think that tantalum carbide has a density of almost 14, so we cannot send them as they are in space. So we have to compromise a bit on the properties and on the specific weight. Moreover, they are expensive to process and machine since they are very hard. So our idea was to combine the fiber reinforcement of CMCs with the ultra-temperature ceramic matrix, such as zirconium diboride or hafnium diboride. And we first started with sintering as our main process. We managed to obtain considerably lower densities than the the individual HTC, still good flexural strength and fracture toughness, comparable with CMCs, intermediate modulus, and we even managed to manufacture bigger specimens. So this is a nozzle. It's not evident from the picture. This is 18 centimeter in diameter, and we also managed to make bolts and screws and a large tile for testing. But still, we are limited in shape because of the sintering process. So in this first study, we will take one reference material. For the UHD phase, we selected zirconium diboride because it has a lower density compared to hafnium and tantalum-based UHDC, and also lower cost. We are talking about 5 to 10 times lower cost. The main additive you will see in all these materials is silicon carbide. So we added it mainly because it improves the sintering of the boride phases. It also improves the oxidation resistance in the intermediate temperature range, and you will see also increases the mechanical properties and marginally decreases the specific weight. However, it's still a liable phase at ultra high temperature, so we will see the differences. So our process starts from the fiber, the UHDC powders, water and a dispersant. So we carry out the slurry infiltration of the continuous fibers. Then with these green composites, we can carry out 3 different processing routes. We can do polymer infiltration and pyrolysis with a phenolic resin, followed by liquid silicone infiltration, or we can directly sinter the material at very high temperature and pressure. Or still, we can do polymer infiltration and pyrolysis cycle with a silicon carbide polymer precursor. The main differences among these 3 sintering consolidation techniques is the following. So for sintering, we have the fiber, which are in black, the zirconium diboride, which is the light gray, and silicon carbide, the dark gray. So what happens in sintering is that when applying the pressure at high temperature, all the individual grains are sintered together, and you can see they're all connected. But in the case of PIP and LSI, what happens is that we create a silicon carbide skeleton in both cases, and you can see the individual UHTC phases are not connected. Moreover, in the case of LSI, we also have some leftover silicon, which in this picture is the intermediate gray, and we also have some reaction at the interface with the fibers. So we fabricated these 3 composites called HP to designate the hot pressing, so sintering, PIP for the polymer infiltration and pyrolysis with the silicon carbide polymer precursor, and LSI for the liquid silicon infiltrated material. We tried to keep the composition as close as possible. Obviously, due to the process parameters and all the variables, it wasn't really possible, but this is as close as we could get. And we carried out some oxidation tests at 1650 degrees C in air at increasing exposure times, so 1, 15, 30 minutes. Take into account usually the application time for these materials is in the range of 2 minutes. So we wanted to explore what would happen for prolonged exposures. So first with the microstructure, this is the sintered material. You can see the fibers are in black. The light gray is the ceramic phase. You can see it's a homogeneous infiltration. This is a unidirectional fiber reinforced material. And when we look at the microstructure, you can see that the individual zirconium diboride grains, they're all connected together with silicon carbide in between all the grains. When we go to the PIP specimen, first we see that there are some infiltration defects. These arise from the slurry infiltration process. And then after we follow up with the polymer infiltration and pyrolysis with the silicon carbide precursor, not always we manage to fill these defects. And so they stay even after consolidation. In this case, you can see that the individual zirconium diboride grains, they are not connected anymore. They act more as a filler. And you can see the dark gray phase in between is the silicon carbide. Finally, for the LSI sample, again, here we have the same issues that we had in the PIP specimen. So these arise from defects in the slurry infiltration process. In this case, the black one is some leftover phenolic, and the light gray is some leftover silicon that went unreacted. And we can see in the microstructure again, the zirconium diboride acts as a filler instead of being connected, and it's everything surrounded by a silicon carbide skeleton. In this case, we also had some reaction with the interface of the fiber, leading to the formation of more silicon carbide. Looking for silicon from EDS maps wasn't really easy, but the XRD confirms without any doubt that there is still some leftover silicon, and quite a bit of it. So on these materials, we wanted first to compare their mechanical resistance. So we carried out some flexural strength testing. And here is a table briefly reporting the results. What we can see is that the sintered and LSI samples have comparable strengths. The PIP sample has the highest room temperature strength, but when we test the same materials at 1500 degrees C in argon, so in protective atmosphere, we see that the only one that managed to withstand this high temperature regime is the sintered material, because the other two, they yield much earlier at around 1200 degrees C, so we cannot even measure the strength at this temperature. Moreover, the sintered specimen sees an increase of strength with temperature, and this was associated to stress relaxation. We also carried out some annealing step on the PIP sample in order to improve its refractoriness at high temperature. And after annealing at 1400 degrees C, we saw actually an increase in the high temperature strength. We were able to measure it, but unfortunately, this came at the cost of the room temperature strength. So there is always a compromise when going for the annealing steps. But in this case, the annealing steps allow the material to be used even at high temperature without failure. On the other hand, for the LSI specimen, the leftover silicon is still the main issue. So we carried out oxidation testing in this kind of furnace. It's a bottom-up loading furnace. Basically, the furnace is heated to the target temperature, which in our case is 1650. Then the specimen is loaded in this sample holder and directly exposed to 1650. So the material is subjected to a thermal shock on the way up and then also on the way down when we take it out of the furnace. And the material is air quenched. So we did increasing exposure times from 1 to 30 minutes. And this is a table that summarizes the oxide thickness for each sample with increasing exposure time. What you can see is that for 1 minute exposures, they're all comparable, very, very slight oxidation damage. But with increasing time, we see that the sintered and the PIP sample, they show comparable performance, while in the case of the LSI material, there is a very drastic change in the oxide thickness, and after 30 minutes, there wasn't really much left over. So let's see what happened. So in the case of the sintered material, we see mainly the formation of a silicon oxide barrier. This is the dark gray on the outside. We also see that the innermost fibers were oxidized and the holes were filled by the liquid silicon oxide. And the light gray phase is always the zirconium oxide in this case. For increasing exposure times, we get a thickening of this oxide scale. And we also see that there is an intermediate layer, which is where there isn't any silicon oxide, silicon carbide, there isn't even any fibers. And when we look at the EDS maps, we can actually see that the light blue one is the silicon signal. We can see that there is the formation of a silicon depleted layer. And this is something that was also seen on bulk zirconium diboride. So it's a it's a known effect. This happens because the silicon carbide is gradually oxidized both to silicon oxide, which goes on the surface, and also on silicon monoxide, which is gaseous and gets removed from the material. In the case of the PAP material, we see a similar behavior. Again, silicon oxide on the surface and an intermediate layer of zirconia and silica, which thickens the more we go up with the exposure time. And even in this case, we see that just for 1 minute, you can see here this very thin layer, which is pore of silicon. And this thin layer thickens as we go up with the temperature. So we can see this effect even in the PIP sample. And finally, for the LSI material, at 1 minute, it behaves even better than the other ones. The only oxide is this thin layer one. But after 15 minutes, we see there is some degradation of the other structure and you can see in the detail that there is no silicon oxide left over here on the surface. It's only zirconia. There is even some leftover fibers, but mostly it's zirconia without any silicon. And this is because the silicon oxide and the silicon, they were removed as SCO. When we look at the EDS maps, this is exactly what we see. We see that there is missing silicon here on the surface, whereas after 1 minute it was still present here on the surface. So we summarize these oxidation mechanisms in the following way. So for the sintered material, after oxidation, after exposure in air, we have the gradual formation of the silicon oxide on the surface and zirconia layer, and the evolution of the volatile boron oxides. And with longer exposure times, we have the progressive oxidation of the material and the formation of this porous intermediate layer where we have the holes and porosity left by the fibers and the silicon carbide. This is very similar to what happens for PIP, but in this case we have the preferential removal of the silicon oxide around the fibers, while we still maintain the fibers intact. And for longer exposure times, the behavior is very similar to the sintered material, always with the formation of the silicon oxide and zirconia layer. So here the zirconium dibride still acted as a protective phase, even if the individual particles were not connected together. But in the case of the LSI specimen, here the silicon is the weak link because we can see up to 1 minute everything is fine. But afterward, the silicon skeleton gets eroded and removed. And so what we are left with is just the individual naked fibers and the zirconium oxide particles that are just laying there without offering any protection. So the material is progressively consumed for longer exposure times. So to summarize this first part of the study, we fabricated 3 different UHT-CMCs based on zirconium dibride and silicon carbide by hot pressing, polymer infiltration and pyrolysis, and liquid silicon infiltration. So sintering leads to the most homogeneous microstructure, also because the sintering process helps in removing any defects that was introduced during slurry infiltration thanks to the pressure. Whereas in the case of PAP and LSI, we still have some intra-bundle voids, which are due to infiltration defects that we were not able to fix with the infiltration techniques. The oxidation behavior is comparable for short exposure times, but it changes significantly for longer times. So generally, the hot pressed and the PAP specimens, they behave very similarly, with the PAP specimen having slightly better oxidation resistance, while the LSI specimen fails already after 15 minutes due to the loss of the silicon skeleton. The room temperature is comparable for all of them, with the PAP specimen showing the highest strength, but the high temperature strength for the sintered material is unmatched, and it's the only one that was able to withstand above 1500 degrees C. And finally, the annealing can impart some high temperature resistance to the PAP specimen, but at the loss of the room temperature strength. So now we will move to graded composites. So we evaluated the two strategies to decrease the overall weight of the material while still preserving the oxidation resistance of the outermost layer. So we explored the two strategies. One was changing the fiber content along the specimen. So this was possible with short fiber reinforced composites, mostly because the processing is much easier. So it's easier to customize each individual layer and then overlap them. So in this case, we kept the macrostructure the same for all the material. So zirconium diboride plus 10% silicon carbide. What we changed was the fiber content across the material. In the other case, what we did was keeping the same fiber amount. So we chose 40% of long fiber, and instead we changed the matrix composition. So we used one layer with zirconium diboride and silicon carbide, and the outer layer with hafnium diboride, which we know from literature is usually has a better performance, but unfortunately it's very heavy and very expensive. So we limited its use only to the outermost layer. And we carried out microstructure and oxidation resistance studies. And afterwards, we also did some strength retention and finally our jet testing. So this is the microstructure of the short fiber reinforced material with the fiber gradient. So here's the low magnification picture. You can see the outermost layer is only the ceramic matrix. The inner layers are made with 20% of fibers, and the innermost layer instead is with the very high fiber content. You can see that the interface is very clean. There is no detachment, there is no spallation. The matrix is the same, and luckily we didn't see any effect of CTA mismatch along the material. There were no visible cracks, and the material was mostly fully dense. And again, we were actually worried that we will get some cracking due to the drastic difference in fiber content, but we didn't see anything of the sort. Also, you can see there is a preferential orientation of the fibers. So along the plane, the fibers are random, but when we see them in the cross section, you can see that they're all lined up like this. This is because this is the direction of the applied pressure. In the case of the composite with a compositional gradient, so here you can see we did the two layers of fibers with the hafnium diboride matrix, which is the light gray phase, while the innermost material was made of zirconium diboride phase. So here you can see the interface. Again, even in this case, the interface was very clean. There was no spallation, there was no cracking, no detachment. And we can see really at the interface between the two phases, we also had some solid solution formation. So thanks to the similar chemistry of the zirconium and hafnium diboride phases, we were able to perfectly join them without any issue, any CTA mismatch problem. And in this case, we were able to perfectly join the two phases together. So we carried out the same type of testing, same furnace, same temperature to test the changes along the material. This is the surface of the short fiber reinforced material with the fiber content gradient. So the surface shows mostly silicon oxide, which is the dark gray, and the zirconia, which is the white. Looking at the cross section, so the main area of interest is really this outermost one, because this will be the one exposed during the application. But we also wanted to compare how the material would have behaved if it was directly exposed as it was. And you can see that in the outermost layer, we have basically the oxidation resistance behavior of a bulk zirconium diboride material with the formation of columnar zirconia and silicon oxide in between. while for the inner layers that contain progressively higher amount of fibers, you can see that the oxidation worsens as we increase the fiber content, which is exactly what we expected, and which is why we reduced the amount of fibers in the most external layer. So this is exactly the kind of improvement we wanted. So by using the bulk HTC on the surface and having the fibers inside. Unfortunately, with coatings, usually you have the issue that the coating detaches from the fiber reinforced materials. But in this case, since the entire material was made with the same matrix, just with the increasing fiber content, we didn't get any of such effects on the surface. When it comes to the long fiber reinforced material with the compositional gradient, so this is the surface. You can see the channels left by the long fibers filled with the silicon oxide. The small particles you see here, lighter gray, this is the apnea. When we look at the cross section, here the oxidation was very, very limited. So it's only this very thin layer. I don't know why the line is not visible, but basically the oxidation stops here in the very first 20 microns, roughly. The behavior is similar to what we saw before for zirconium diboride. So the formation of silica on the outside with some apnea grains. And on this material, so we were surprised by the very high oxidation resistance, and we also wanted to carry out some strength retention tests to see how the material mechanical properties behaved before and after oxidation. So we did the 3-point testing of the materials before and after oxidation. So we put the hafnium diboride layer on the bottom, so under tensile, and we investigated the strength before and after oxidation at room temperature. So what we saw between these two materials, the behavior was pretty much unchanged. Same shapes of the curve, same slope of the curves. The only difference was in the actual final value. There was a decrease of roughly 10% in the strength. And this was mostly attributed to the oxidized cross-section. So basically, it was attributed to a reduction of the effective cross-section under bending. So assuming that the oxide did not contribute to the strength. Finally, always on this material, which was the most promising, we wanted to carry out some extra testing. So this is an arc jet wind tunnel facility at the University of Naples, and they did some testing at a very high temperature, above 2000 degrees C, with very high energy. And we also compared this material with the previous one that we tested in the same facility, and that was only comprised of zirconium diboride silicon carbide, to see the difference between the two. So this is the reference material. This is this button shape you see here. It is basically mounted here and is directly exposed to the heat flux. And so the white is the oxide. And when we inspected the cross section, we could see the following layering. We had a porous outer layer of zirconia without any silicon oxide, an intermediate zirconia and silica layer. Then the innermost layer was porous, again without any silicon or fibers, mostly voids and zirconia. And finally, the unreacted material. And the overall oxide thickness of these materials was roughly 360 microns. We carried out the same testing on the graded composite with hafnium diboride on the top. Here you can see an optical microscope of the cross section of the specimen. I don't know if you can see here, but here is where the hafnium diboride layer starts. and only the very first layer was oxidized, which is the very white one. The layering was pretty much the same as zirconium diboride. So again, another layer of hafnia, inner layer or hafnia, and some silicon oxide, which is this dark gray here. Then an intermediate porous layer, and finally just the hafnia, the hafnium diboride with the carbon fibers unreacted. And what we saw was a decrease in the oxide thickness of about 25%. So in this case, to summarize the oxidation mechanism, up to 1600 degrees C, 1650, what we end up is usually the material with an outer silica layer, intermediate zirconia and silica layer, and then this silicon depleted layer. And this is pretty much the same behavior from zirconium diboride and hafnium diboride. What changes above 2000 degrees C is that the outermost silica layer is removed, which leaves us with the outer porous zirconia or hafnia layer in our last case. So to summarize for this study, we successfully produced HTCMCs with both fiber gradient and compositional gradient. All the layers were perfectly jointed with varying fiber or composition with no spallation defects. We were able to improve the oxidation resistance while also decreasing the specific weight. So we were able to keep a lower density matrix in the inner layers and only use the high performing hafnium diboride 1 on the very outermost layer. And on this same material, thanks to the promising performance, we carried out some strength retention tests. We were able to retain up to 90% of the strength. And finally, our jet testing confirmed the better performance of the hafnium diboride layer with an improvement of about 25% compared to a reference material with only zirconium diboride. So to conclude, we compared the three different processing techniques, showing how sintering still leads to the highest high temperature mechanical behavior, while PIP is also very promising, a slightly higher oxidation resistance, and can be made to withstand even high temperature at the cost of the room temperature strength. The use of degraded structures allows us to retain high temperature performance without compromising the property of the material or unnecessarily have high density across the entire specimen. And finally, strength retention tests carried out on the compositional graded HTCMC show a decrease of about 10% of the mechanical properties compared to room temperature, which was mostly attributed to a reduction of the cross-section. And finally, our jet testing confirmed the effectiveness of the hafnium diboride layer to decrease the oxide layer thickness. Thank you very much for your attention, and if you have any questions, I'm available.
Thank you, Dr. Vinci, for this nice presentation. And I'm looking the Q&A's box for the questions. Right now, there is no question, but I'm sure there will be. Yes. Oh. So I'm looking right now. So maybe I can ask a question about the short fiber composites. So are those the carbon fibers, right? These short
Yes.
fibers. And according to the hot pressing or the PIP, I couldn't catch the names properly, but there are some orientations of these fibers, right?
Yes. So the
And
fibers are they
are
are
they
random.
along in in plane direction?
So in plane direction, they are randomly oriented. But if you
Hmm.
look at the cross section, like here, you can see that they are oriented preferentially along this plane.
Hmm. I see.
This is because of the applied pressure that comes from the bottom and the top. So all the fibers are, let's say, pressed in this in the orthogonal direction. And so you can see a preferential orientation here, but I don't know if I have a picture of the top. Now,
Okay.
basically, if you look at the top side, they look like this.
I see.
So they're all randomly oriented. But when you look at the cross section, they have a preferential orientation in the Z axis. This is
Okay.
because
Thank
of
you.
the applied pressure.
Thank you. And in one question, to Paul Brun asking that, did you notice any fiber degradation in your hot pressed CMCs relative to the two other processing methods?
So there is some fiber degradation. It's mostly mechanical because the specimen is sintered at 1900 degrees C and 30 MPa of pressure, and this inevitably leads to some degradation of the surface. Sometimes it's of chemical nature when we have more reactive phases. In this specific case, with just silicon carbide and zirconium diboride, there is some very, very slight reaction. You can see like here and here and here on the very tiny bits. And this is some reduction that occurs between the oxides naturally present on the HTC powders and the carbon of the fibers. But this is usually very limited in the case of the sintered material because it's not as reactive. While in the case, for example, of PAP with a silicon carbide precursor, this is more evident. You can see here that there is an agglomeration of silicon carbide all around the fiber, or even here. And this is much worse in the case of the LSI sample. You can perfectly see the silicon carbide rings around the fibers. So usually this effect is more pronounced for the latter two processes and less so for the sintered materials. But yes, we still do get some degradation. But in order to, let's say, minimize the effect of this, we use high modulus fibers. We tend to be more refractory towards these processes.
Okay, thank you. And for the time-wise, I think we should skip the last question. And thank you for both presenters for today's webinar.
Thank you.